Greetings, my name is Tuomas Orponen and you are watching the first lecture on the course Introduction to Fourier Analysis. Here you can see the functions cosine and sine. The main philosophy behind Fourier analysis is that these are the only two functions you will ever need. To justify this philosophy, we would like to express an arbitrary complex-valued function on the real line as a complex linear combination of the functions cosine and sine. Note that the functions cosine and sine themselves are real valued, so if f is complex valued, we will have to allow for complex coefficients in the linear combination. Literally speaking, it is not possible to express every function f as a linear combination of the cosine and the sine functions. The first evident issue is that the vector space spanned by the cosine and the sine functions is just two-dimensional, but overall the space of continuous functions on the real line is infinite dimensional. To overcome this issue, let's also allow for the functions x map to cosine nx and x maps to sine of nx for all natural numbers n. In this figure, you see a picture of the function cosine 3x. This function looks very much like the standard cosine function, but it oscillates faster. Now, the space of all linear combinations of the functions cosine nx and sine nx when n ranges in the natural numbers is over the infinite dimensional. So, at least in theory, we have a chance to express an arbitrary function f defined on the real line as an infinite linear combination of the following form. F of x equals a sum over the natural numbers of an cosine nx plus bn sine nx, where the coefficients an and bn are arbitrary complex numbers. Such an expansion of f is known as the Fourier series of f. Many natural questions arise. What do we have to assume about f that such a Fourier series exists? If the Fourier series exists, how well does it converge? And what can we say about the coefficients an and bn? And finally, what can we concretely do with the Fourier series expansion? Stay tuned on the course to find out. There is another problem about Fourier series expansions which I would like to next mention. If you pick any natural number n, then the functions cosine nx and sine of nx are always 2 pi periodic. This means that the cosine of n multiplied by x plus 2 pi is the same as the cosine of nx for any x in the real line. And a similar formula also holds for sine. It follows that also every linear combination of the functions cosine nx and sine of nx is 2 pi periodic. Hence, it is impossible to represent a non-2 pi periodic function f on the real line as a Fourier series of the kind we saw above. So, is Fourier analysis strictly restricted to 2 pi periodic functions? No, it surely is not, but things do get a bit more complicated without the 2 pi periodicity hypothesis. Here's the rough idea. The functions cosine of nx and sine of nx are indeed 2 pi periodic when n is in the integers. But the same is not in general true when n is equal to xi is just a real number. In other words, if you take some x on the real line and then you compute cosine of xi times x plus 2 pi, then this need not agree with cosine of xi x. This would only be true if xi is an integer. So, if in addition to the natural numbers we also use other frequencies xi on the real line, there is again a chance to write the not necessarily 2 pi periodic function f as a Fourier integral. So the Fourier integral representation of f would have the form f of x equals the integral of a xi times cos xi x plus b xi sin xi of x dx. This is really just the integral analog of the Fourier series representation where we were just summing over the natural numbers. The functions a and b are arbitrary complex-valued coefficient functions. There are many questions concerning this Fourier integral expansion which are similar to the ones we encountered a bit earlier regarding the Fourier series expansion. For example, what kind of functions f admit such a Fourier integral representation? And then what can we say about the convergence of this representation? What can we say about the coefficient functions a and b? On the first part of the course, we will mainly focus on the questions regarding the Fourier series, and then later we will also treat the Fourier integral. The third problem about Fourier series expansions is mainly an aesthetic problem. The expression of the Fourier series using the cosines and the sines might look a little ugly. So is there a neater way to write it down? Yes, there is. There is an incredibly powerful shorthand notation for the cosine and the sine functions. This shorthand notation is known as the complex exponential function. For any real number x, we define e to the power ix to equal cosine x plus I of sine x. You may have already encountered this notation on a basic course on complex analysis. This is just the definition for the notation e to the power ix. The beauty of this notation lies in how incredibly well it works. For example, with this notation e to the power I psi x, if you differentiate the function e to the power I psi x with respect to the variable x, the result is I times psi times e to the power I psi x. So this is exactly the same formula which you might expect from the usual exponential function. Another useful formula to keep in mind is what happens to e to the power ix when you raise it to an integer power. One can compute that e to the power ix to the power n equals e to the power inx for every integer n. Proving this formula is left as an exercise. You can do it by induction. The formula is known as the de Moivre formula. As a further exercise, one can check that every linear combination of the cosine and sine functions of the form sum little n runs from 0 to big N, an cosine nx plus bn sine of nx can be rewritten in the form sum little n runs from minus big N to big N, cn times e to the power inx, where the cn's are complex coefficients determined by the coefficients an and bn. It follows that if a 2-pi periodic function f on the real line taking complex values admits a Fourier series expansion in terms of the cosine and sine functions, then it also admits a series expansion in terms of the functions e to the power inx. So we may write fx equals to the sum over the integers cn times e to the power inx. Note that I'm not claiming here that every function f would admit such a representation. I'm just claiming that if a function f admits a representation in terms of the cosine and the sine functions, then it also admits a representation in terms of the functions e to the power inx. It turns out that the coefficients cn in the second representation for f are unique. They are known as the Fourier coefficients of f. They are often denoted by cn equals to f hat of n for n in the integers. Moreover, it also turns out that the Fourier coefficients have a fairly simple explicit formula of the following form. F hat n equals 1 over 2 pi times the integral from minus pi to pi fx e to the power minus inx dx. If f is not 2-pi periodic, then, as we discussed earlier, f cannot possibly have a Fourier series expansion. In this case, the analog of the Fourier coefficients would be the so-called Fourier transform, which is f hat of psi equals the integral over r of fx times e to the power minus I psi x dx. There is one more problem which I would like to mention here. What about functions defined on higher dimensional Euclidean spaces Rd? It turns out that defining Fourier coefficients and the Fourier transform for functions defined on Rd is not really a problem at all. One only needs to replace e to the power inx by e to the power in dot x, where n is an integer vector and x is a real vector. The dot refers to the standard Euclidean dot product. So the dot product between two vectors x and y would be the sum of the products of their components. With this notation, the Fourier series expansion of a 2-pi periodic function defined on Rd would look like the following. F of x equals the sum over all integer d tuples n cn times e to the power in dot x, where the cn's are complex coefficients. These coefficients are still known as the Fourier coefficients of f. Now that we have introduced the Fourier coefficients, let's see a little of the history of the topic and also an informal application. As you might guess from the name, Fourier series were introduced by Joseph Fourier as early as 1807. Fourier had served in Napoleon's army until around the year 1800, and then in 1801 Napoleon appointed him as a governor of a region around Grenoble in France. The day job of the governor was to supervise infrastructure projects such as road constructions. But on his free time, Fourier also pursued some purely mathematical topics. He was particularly interested in solving the heat equation. The heat equation is a partial differential equation which concerns a function of two variables. These variables are x and t. The variable x ranges in the interval from -pi to pi and is often known as the spatial variable. The variable t ranges on the interval from 0 to infinity and is often known as the time variable. The heat equation is solved by any function u in these two variables x and t, whose second x derivative equals the first t derivative. To make the solution of the heat equation unique, one also needs to prescribe a set of initial values. By definition, these are the values of the function uxt on the x-axis. These values are often denoted by u0, hence u0 of x equals u of x0. From the physical point of view, the heat equation models how an initial heat distribution given by u0 on the interval from -pi to pi develops over time. If you want, you can think that the interval from -pi to pi represents a narrow steel stick of length 2π. Then the value of the function u0 at the point x tells you how warm this steel stick is at place x. As time passes, this initial heat distribution u0 starts to even out or smoothen along the steel stick. Assuming that the function u satisfies the heat equation with initial data u0, the distribution of heat at time t is given by the function u of tx equals uxt. The heat equation is a fundamental partial differential equation which, as Fourier observed in 1807, can be solved using Fourier series. Let us now see the rough idea of this solution. I already apologize for the lack of details. So what we would like to do is to find an explicit expression for u, assuming that u satisfies the heat equation with initial data u0. Assume, without any special justification, that all of the functions ut defined a bit earlier can be expanded as a Fourier series. In other words, for every fixed t, the function ut can be written as ut of x equals the sum over n runs in the integers cn of t e to the power I n x, where the c and t's are the Fourier coefficients of ut. It may or may not be plausible to assume that such a Fourier series representation for ut exists. But now, for the sake of this illustration, let's just assume that it does. Moreover, let's assume that these coefficients c and t are so nice that they are even differentiable in the t variable. So by this I mean that the derivative of the function t maps to c and t exists. If this happens to be the case, then both the x and the t derivatives of the function uxt can be expressed in terms of this Fourier series. I recall that in the heat equation we were mostly concerned with the second x derivative and the first t derivative. Now, using the Fourier series expansion, these two derivatives can be expressed as follows. The second x derivative of uxt equals minus sum over n runs in the integers n squared c and t e to the power I n x. Whereas the first t derivative of uxt equals the sum over n ranges in the integers, the t derivative of ct times e to the power I n x. These two formulas follow immediately by differentiating term by term the Fourier series expansion for utx. But I would nevertheless like to warn you of the missing details here. First of all, as we already pointed out, it's highly questionable if the c and t coefficients can be differentiated with respect to t. But second, it's also not clear whether this Fourier series expansion converges uniformly and hence the term-by-term differentiation is allowed. Once again, just for the sake of illustration, let's assume that all of this works out. In this case, we may write as follows. First, recall that u solves the heat equation. Hence, 0 equals the t derivative of uxt minus the second x derivative of uxt. And further, by the two formulas which we have just derived above, this difference equals the following sum. So, now we have reached the conclusion that this kind of a series equals 0. And this conclusion holds for every x on the interval from minus pi to pi and for every non-negative value of t. Now there is a separate result which says that if such a series vanishes identically as we have just seen, then in fact all of the coefficients of the series must also vanish. If we write what it means for these coefficients of the series to vanish, we get the following equations. The t derivative of the coefficients c and t plus n squared times c and t equals 0 for every integer n and for all non-negative t's. And if this equation is rearranged, then we find that the t derivative of c and t equals minus n squared of c and t. And once again, for all integers n and for all non-negative t's. What we have on this line is an ordinary differential equation for the function c and t as a function of t. It is not difficult to solve this equation, and the solution is given below. Cn of t equals an times e to the power minus n squared t, where an is an arbitrary constant. Finally, the precise values of the constants an can be determined from the initial values u0. It turns out that the constants an are actually the Fourier coefficients of the function u0. To see this, first expand u0 of x in terms of the Fourier series. So u0 of x equals the sum over the integers cn0 e to the power in(x). Next, recall that we already solved that c and t equals an times e to the power minus n squared t. So if you plug in this formula here, and then you substitute t equals to 0, you eventually find that u0 of x equals the sum over n runs in the integers an times e to the power in(x). But now, by the very definition of Fourier coefficients, an equals the nth Fourier coefficient of u0. After these tricks, we can now finally write an explicit expression for the function uxt. First, recall that uxt equaled its Fourier series. Uxt equals the sum over n runs in the integers c and t times e to the power in(x). And finally, substitute the solution for the coefficients c and t, which we just found above, to find that the sum can be rewritten as the sum over n ranges in the integers, the Fourier coefficients of u0 times e to the power minus n squared t times e to the power in(x). Now, if you look at this equation which we just derived, you see that on the right hand side, everything only depends on the initial data u0. This means precisely that we have found a solution for uxt in terms of the initial data u0. This solution may not appear very explicit, but it's nevertheless a solution. It could be calculated or at least approximated by a computer who can compute the Fourier coefficients of the initial heat distribution u0. This concludes our introduction to Fourier analysis, and on the next lecture we will begin a more rigorous study of Fourier series of 2 pi periodic functions on RD. Thank you for watching. Goodbye.